Okay, we are on the third video here in section 12.1, continuing our discussion here on creating confidence intervals to try to estimate where the true population slope is located. It's the slope that kind of tells you how your two variables are associated with each other. If that slope is positive, then your variables have a positive association. Obviously, if the slope is negative, they have a negative association. So there was an example a few pages back where we were looking at dropping these paper helicopters at various heights. That's what our explanatory variable is going to represent in this problem. And then the response variable, the y, is going to represent the flight time, which is in seconds how many time or how long that helicopter kind of stayed in the air. It says here that the number of helicopters for this experiment was 70. Again, this is going to be really good practice in us trying to dissect the pieces of information that we get when it's presented in this computer output format. So there's kind of four parts to this problem that we want to answer here. Part A says, give the standard error of the slope. Okay, and that's that symbol SE sub B. And then we want to interpret what this value is. So we want to be able to pull this value, the standard error of the slope, out of this computer output. So again, you want to think through, okay, this column here is labeled standard error. It is this row here that is describing everything about your slopes, and this row here is describing everything about your y-intercepts. So if we want the standard error of the slope, we would be looking for where that standard error coefficient column collides with our slope column. That would be the number 0.0002018. So for part A underneath here, I'm going to go ahead and just report that the value of the standard error of the slope is that number there. And then we want to interpret, like, what does that mean in the context of this helicopter problem? Okay. So we're going to say if we repeated this process many times, the sample slope would typically vary by, and then here's where we're citing what that standard error of our slope is. It would typically vary by about 0.0002018 from the population slope, which we use the beta symbol to represent that. Okay? So if we were to kind of repeat this over and over and over again, it kind of feels like this is a really small standard deviation here. We're only expecting our sample slopes for various regression lines we would create from a sample of our data to really just be off by about this really small number from what the true population slope is. So that's part A. Okay, part B says, find the critical value. Okay, critical value, those are your z-scores, your t-scores, for a 95% confidence interval for the slope of the true regression line. And then we want to calculate that confidence interval, show our work. Thank goodness we have this addition here, which says we're going to just assume that the conditions have been met. Okay, so our first step is to get that t-score. Okay, we said this was a 95% confidence interval. So if it's a 95% confidence interval, that remaining 5% would need to be split in half shared between each tail here. So that's the area to the left, if I'm wanting this left t-score first. Okay, and then I want to put the degrees of freedom. Remember, degrees of freedom on this, it's sample size minus 2 when we're doing these inferences on slope. So 68 is the degrees of freedom, and that's going to yield a t-score of 1.995. Okay, that is our t-score. The other part to this was asking us to actually construct the confidence interval. Well, here would be the generic version of how that formula would look. the statistic, which is the slope, plus or minus our t-score, we just calculated, times the standard error of the slope, which we wrote down in part A. So we need to look back up at the computer output and see if we can pull the correct sample slope value from this computer output. Again, we said that slope rho, drop height, is what our x variable is representing, where that collides with the coefficient column, that represents your slope. Okay, so I'm just going to label it on here. We said this was the standard error of your slope, and this value here is actually the slope itself. That'll be the very center of our confidence interval here that we're constructing. So I'm just going to put these substitutions right underneath our variables here. That's our B, t-score, and then our standard error of our slope. Okay, if we type that in with a plus and a minus, we end up getting the interval to be 0.00532 to 0.00613. Every time we construct confidence intervals, we always interpret them. We would say on part C, I believe that's what it was asking us to do here. Anyhow, interpret the interval from part B in context. So we want to say that we are 95% confident that the interval, we're going to list that interval here, captures the true population slope of the regression line. If you stop there, you haven't actually put any context to this answer at all. So you want to make sure it's the regression line that is relating drop height and flight time. Just kind of denote what your two variables are so that you've allowed for a little bit of context here in the problem. And then part D, which I have filled in here, it just says explain the meaning of being 95% confident in context. Okay? What they're really asking for here on part D is they're asking you to explain what we mean by the confidence level. Okay, sorry. By the confidence level, okay? They want to know what we mean by that. And so I want you to know this. In this answer, there is no mention of the actual interval. When you are describing the meaning of being 95% confident, you're essentially saying that if we were to repeat this process over and over again with the same sample size of 70 helicopters, we would expect that 95% of the intervals are going to capture the true population slope of the regression line. Okay? We do not say we're 95% sure that that interval we just created, 0.00532 to 0.00613, we're 95% sure that that captures it. That is not what a 95% confidence level means. It means if you repeat it over and over and over again, and if you guys recall when we did this, I pulled up an applet where that vertical line represents where like the true, we'll say the true population slope would be located. And then we create these different confidence intervals. And we're hoping that most of them catch it, but occasionally you get one here that misses it. But we're saying 95% of the time we expect the intervals that we create, we want 95% of them to correctly capture where that population slope is at. Okay, let's flip to the next page, and I'm going to show you the calculator feature that runs this particular t interval for these slopes. Okay, now here is what it is actually called on the calculator, linear regression t interval, and we are going to go ahead and just flip back to a couple examples here on a few pages earlier to just kind of run what we already have on our paper. We're going to do it on the calculator here. So here's one thing that you have to make sure when you're running this linear regression t interval. First of all, this is probably obvious, you have to make sure that all the raw data is typed into L1 and L2. And then secondly, before you run this linear regression t interval, you have to have ran a linear regression prior to that. Okay, when you run that regression, that's what stores the residuals into your calculator. Okay? So you have to do that part first. And so we're going to backtrack here to just, I think it was the example right here where we had put all these rows and scores into L1 and L2. And I believe on the very next page, we were, actually, I don't know. Did we, maybe it was the next page. It was. Okay, it was this page at the bottom here. Okay, we're going to use this data here, which is the same data from the previous page there. We had constructed this 90% confidence interval, okay, right here. Okay, so we're going to compare that answer with what we're going to get when we do it on the calculator. Okay, so hopefully you already have that row and test score data in your calculator, like just stat edit. I'm going to just clear out L3 here. Okay, so that's all there. I'm just real quick going to rerun my regression just to make sure all that's stored nicely into the calculator. Stat, calculate, option 8. Come down here with the VARS button and put Y1 there. Okay, now, if I want to construct a confidence interval, 90% confidence interval, I'm going to stat. I'm coming over to tests, and it's actually all the way towards the bottom. It's called linreg, linear regression t-int, int for confidence interval. Okay. I need to tell it where the data is, L1, L2. I need to tell it what the confidence level is. I'm doing 90%. Then you can just bump all the way down to calculate, and it should spit out for you. The nice thing is it will report to you the degrees of freedom. We always want to make sure we write that down. But you can see at the top there, it also gives you the confidence interval, which is close, maybe slightly different than what we're seeing when we did the example here, when we pulled it from the computer output, but that's definitely sufficient enough. And they gave you some values to be able to actually create like your regression equation. But what we're really after when we run this on the calculator is just getting what the confidence interval is. So I just wanted to talk through how that's the command on the calculator that you would use to create a confidence interval for the slope. Okay, so let's go ahead and take a look at this next example here. Okay, this example is talking about how everybody knows that cars and trucks lose their value the more that they're driven. Can we predict the price of a used F-150 Super Crew 4x4 if we know how many miles it has on its odometer? So we have this random sample of 16 used Ford F-50 Super Crew 4x4s were selected from among those listed on a sale on autotrader.com. Okay, the number of miles driven and the price in dollars were recorded for each of the trucks. You can see there's 8 given in that first table, and then there's another 8 in the second table. Now here's the good news. Most of this data is provided for you. I did give you the raw data. You do not need to type that into your calculator because I have all of these graphs already provided for you. And again, this is what I often see on these problems is I've seen a lot of free response questions that kind of already give you, hey, here's the residual plot, here's the original scatter plot, there's a histogram of your residuals. So let's make sure we're comfortable with what we're looking at here. This first graph right here is your original scatter plot. Those are your 16 points, taking how many miles were on those trucks and what the price of the truck was. Okay. This middle one here, this is representing a residual plot. Okay, a residual plot. And then this third one here is a histogram of the residuals. Okay, histogram of the residuals. Okay, so we have those 3 things that we're going to need to reference, maybe do a little bit of this here. Okay, then we have some nice computer output also, which is always helpful because then it's a way of sidestepping some of those formulas to calculate the standard error of the slope because we can just grab the value from this computer output. So it's asking us to construct and interpret a 90% confidence interval for, and here's what we'll be defining, Okay, for the parameter, the slope of the population regression line. Okay, remember when we do confidence intervals, we kind of categorize this process as a state plan, do, conclude. So what we're going to be doing is we are looking to estimate beta, which is, and I'm just going to write what I underlined right above. Maybe I'll say this is the true slope of the population regression line. And I really should be a little bit more specific and say relating miles driven and price. Okay. In the plan step, this is where we list our conditions and we also name the test. Okay. List the conditions and we name the test. I'll go ahead and list the name off to the side here. Okay. This name for this test is called a t-interval for slope. I suppose you also could call it what's on the calculator screen, which is linear regression t-interval. Okay, to check off the linear condition, we want to look at our residual plot and make sure that the residual plot shows no evident pattern. And that middle graph there, I don't see any distinct pattern happening there. It looks pretty scattered. So we're just going to fill in here. It shows no evident pattern. This was not an experiment. A lot of our problems have been. They did actually take a sample of 16 trucks. We need to show that 10 times 16, 160, that's definitely less than or equal to all the F-150 trucks that they could have chosen. Okay, so we're good there with the independence. The N, the normality check, is when we are looking at this right graph. We are looking at this histogram of the residuals. Okay, just trying to make sure that this feels like there's, somewhat of a normal curve to this, no weird skewness or outliers. We want it to be at least approximately symmetrical of sorts. So we're going to say that the histogram of the residuals is, you can either say approximately normal or you can say approximately symmetrical. Either way is fine, with no extreme skewness or outliers. Okay, the next condition is where we're looking for that equal variance there. We're looking back at the residual plot, making sure we don't see any weird fanning out left to right or right to left. I'm not seeing that at all. It feels like those vertical distances are kind of equal here. So we're going to say that the residual plot shows equal amounts of vertical scatter across the x values. Okay? Equal amounts of vertical scatter, and then the R is that the sample was taken randomly. Okay, so now to the do step. Now, I'm not going to put all that data into my calculator just so I can do it on my calculator. It actually will be much faster if we just pull the values from that computer output and plug them into this formula. So we need to go back up to the top and we need to make sure we pull the number that represents what the slope of that sample regression line would be. Remember, this is the row that is slope. Right here would be our slope. And then this right here, so this is our sample slope. This is our standard error of our slope. We want to use those two values below here, and we'll need to fill in our t-score as well. Okay? So negative 0.16292 for our slope, 0.03096 for our standard error, and then t-score, we said we were doing a 90% confidence interval, so extra 10% is split in half, area to the left, degrees of freedom, n minus 2. There were 16 trucks in this sample, so degrees of freedom would be 14. I'm going to use 1.76 as the t-score. That will give a confidence interval of that. Now, I filled this template in for you, but you need to be comfortable with kind of drafting this yourself, saying we're 95% confident that this interval captures And then whatever your definition was up there in the state step, the true population slope beta relating miles driven and price. Okay, that's essentially what we're doing here. Okay. If you are feeling comfortable with this, I think that we will go ahead on the next page. This is yet another example, very similar. It does give you the raw data set, but you have all of these nice graphs to kind of look at and the computer. If you feel like you need another example to practice, you can go ahead and do this one. I'm not going to do this one here. This would be a fine place, I believe, for us to go ahead and stop. And there's some examples on page 762, I believe 13 through 17 odd, that you can go ahead and try that go along with this video.